Okay, thank you, students. You know already me. I am a Dr. John Jeparaj, and my cell phone I am giving here 9443505110. So in this class, we are going to discuss about the group in mathematics. What is a group? G-R-O-U-P group. Okay, it is nothing but a set with some binary operation satisfying these three conditions is called a group. So a group is nothing but a set with some binary operation, and that binary operation should satisfy all these three conditions. Okay, I have to explain this, then only you will understand that. Suppose A is a set. You suppose A is a set and star is a binary operation. You know what is a binary operation? Am I correct? Binary operation means an operation between two elements only is called a binary operation. Okay, right. This algebraic structure A comma star, that is a binary operation, is called a group. Is called a group. If the binary operation should satisfy these three conditions: associativity, existence of identity, and existence of inverse. Okay, right. Now what is the meaning of this associativity? Okay, right. Now I will explain that what is meaning of the associativity. You take any three elements here, A comma B comma C belongs to the set A. Okay, all these elements belongs to the given set A. Right? Right. Now I am associating A and B with respect to this binary operation first. First I am associating the first two elements A and B by this operation. Then again I am associating this resulting element with the last element B. Last element B. Now instead of this particular order, sorry, this is C. Okay, I made the mistake there, and I have to erase that. Yes, I have to erase this. Coming back, and I will take that and ink white I will take. I am taking the third element. Okay, C. Now I am changing the order. First I am taking the B and then operate this binary operation. Operate this binary operation on C. You will get a resulting element, and that particular resulting element must associate it with the first element A. Okay, you give importance here, and listen here carefully. This association is first element associated with the second element with respect to the binary operation, and then third element is associated. In this case, second element, third element is associated first, then afterwards the first element is associated. For any three elements, A comma B comma C, I see that both are equal. Okay, what's the meaning here? You can associate the elements of A in any order, but the resulting element is same. The resulting element is same. This way of associating in any way, but the resulting element is same, is called the associativity of this particular binary operation with respect to all these elements belongs to the set A. Okay, right. Now what is the next property should be satisfied here? That is existence of identity. Existence of identity. Okay, what is existence of identity? There should exist a single element. That single element I am taking as E. A single element E that should also belongs to A. Okay, there should exist single element E, and that should belongs to the set A. Okay, implies for any A, for all A. Okay, for all A belongs to the set A. For any A, the set belongs to A. We have that A binary operation operated on E. We should have E binary operation acted upon A, and we should have the element A. So what you understand is that you take any elements, okay, if you operate it with this particular element by this binary operation, we are getting the same element A. We are getting the same element A. Okay, if that is the case, if there exists a number like this E, it is called an identity element. What we say, this element is called identity element. Identity element, we say. So there must exist an identity element in this particular set with respect to this binary operation, and this particular condition we call it as existence of identity. Okay, so this is associativity. And this is called existence of identity. Now what about the existence of inverse? Okay, right. For all A belongs to the set A, okay, there should exist a single minus A, such that that is very important, such that if this element is operated on this element with respect to this binary operation, this element is operated on this by this binary operation, you should have an identity element. That is, this element is operated by the binary operation on this particular element. You should have the identity element. And that also equal to say that this element is operated on A. You should have the identity element E. So like for every A belongs to A, there exists an element minus A, such that if this element and this element is operated on by this binary operation, then you will have the identity element. Okay, identity element. Otherwise, if this element minus A, for every minus A, we have an A belongs to A, such that minus A is operated on A by this binary operation, we will have the identity element. If there exists an minus A for each and every A belongs to A, then we say that inverse exists for A. So for each A, we have different inverse exist. So you must note that the identity element is unique in any group, but the inverse is different according to the different elements. Okay. Now, if a set exists like this with a binary operation satisfying these three conditions, then this algebraic structure, the set comma the binary operation, we call it as a group. So a group is nothing but a set with binary operation, and the binary operation should satisfy associativity, existence of identity, and existence of inverse. Okay, so this is what we call a group. Okay, right. Now coming to the next slide, some examples I am going to show it to you, and I am going to prove you how this set with some operations, we call it as a group. Okay, so we are giving some examples for a group here. The set Z of integers form an abelian group with respect to usual addition. Okay, abelian group or group is abelian means a commutative. Okay, group with usual addition. So what's the meaning of this actually? We have to prove that Z, that is a set of positive integers with the usual addition, this is what a group we have to say first. So if it is commutative, definitely it is an abelian group we say. Okay, so let us prove that Z comma plus this mathematical structure, algebraic structure, is a group or not. That is, we will prove first, then afterwards we will prove that it is abelian group. Okay, right. So to say that this structure, an algebraic structure such that inside the bracket a set is there with some mathematical operation, in this case plus a group, we must show that they satisfy the associativity and then existence of the identity and also the existence of inverse for each and every element. That's what we have to prove here. Okay, so first let us prove associativity. Okay, we will prove that associativity satisfies or not. I'm shortly writing associative. Right. Now associative among what? Among the three elements or more than three elements associated in any way, the resulting element is same. That's what we have to prove here. Am I correct? Okay, so let us take this particular associative property. Okay, so in this set Z, suppose A comma B comma C belongs to Z, which implies definitely first you are associating A with B, then you are associating C. Okay, right. This is one way of association of the three elements. Now other way I am associating B I am taking and C I am taking and making association with respect to binary operation, that is here plus. Then I am associating the first element with respect to plus. What I see is that both are equal. Both are equal. Definitely, there is no doubt at all. Take for example here 2 plus 5, because 2, 5, 7 is associated first, then you suppose 1. Okay, here associating the last two element 5 plus 1, 5 plus 1, and then I am associating the first element 2. Now 2 plus 7, 2 plus 5, 7 plus 1, and that side what I have there 2 plus 6. What I get here 8. So 8 is equal to 8. Okay. So for three elements 2, 5, 1, I see that this particular associative law is true. So like this, for any three numbers belongs to Z, the set of integers, definitely this condition will satisfy, and thus the associative property is satisfied. The next one is about the existence of the element. Existence of the element. I mean the identity element. Am I correct? Or identity element or existence. EX. IS. Existence. Existence of identity. So what's the meaning of existence of identity? I told you just before that there should exist a number, or there should exist an element E belongs to Z, such that for all the elements in this particular set, if that element is added with E, we must have the same element. Am I correct? If there exists an element like that, then that is called identity. Okay. So here there exists E. There exists E belongs to Z. Belongs to Z. Such that, which implies, okay, for all A belongs to Z implies A plus E implies A plus the binary operation E equals E. It is true, am I correct? Yes, so what is that number? Can you tell me? You should have a number in Z such that if you add all the elements, then you should have the same elements. Okay, such a number we have to identify. Can you tell me that element here? Yes, 0 belongs to Z implies for any element. I am taking one element as 5. Then add that element with 0. What you will get is 5. So whatever the number you are taking, add with 0, you will get the same number. Okay. Therefore, there exists an identity in Z such that any element operated by the operation, here binary operations plus, with that particular 0, you will get the same element. Okay. Therefore, there exists an identity. The next condition is that the inverse. For each and every element, there should exist an inverse element. Am I correct? So let us discuss about that. Inverse. Can you tell me here what is that? Is that a set of integers? Therefore, there exists. Am I correct? Here, for all A belongs to Z. For all A belongs to Z, there exists A minus A belongs to Z, such that or implies A added, I mean here binary operation added with this minus A, we get the identity element E. Am I correct? Yes, for each and every integers, we have a negative integers like that. If you add this and this, definitely we'll get the identity element. Here the identity element is what? 0 is the identity element. Am I correct? Take for example, I think 10. 10 belongs to Z. Am I correct? Yes. So 10 belongs to Z. And minus 10 also belongs to Z, because a set of integers belongs to Z. If you operated the binary operation here on both of these, okay, so what will get? 10 plus minus 10, you will get 0. What is the 0? 0 is identity element. Am I correct? So I have taken one element, 10 belongs to Z, and I shown that there exists another element minus 10 belongs to same Z, such that if we operated this 10 on this minus 10 by the given operation plus, I am getting 0. 0 is what? That is the existence of identity. Am I correct? So like this, for each and every element A belongs to Z, we have some elements minus a, not some elements, like only one element minus a, such that a plus minus a equals the identity element. Okay, so now you come to this particular structure, algebraic structure. So this algebraic structure, I mean the integer set with the usual addition is a abelian, is a group, of course. It's a group. Okay, but here you see that the commutative law also satisfies. Am I correct? Commutative law is also satisfies. How it is satisfies? Suppose a comma b belongs to the set of integers. Then what I see is that a binary operation operated on b is equal to b binary operation plus added upon a. So this is true for all two elements belongs to Z. Am I correct? Yes. Take for example 5 plus 2. 5 plus 2 equals 2 plus 5. So we have that 7 equals 7. 7 equals 7. So both are equal. So this particular property we call it as a commutative property. So if a given group satisfies this commutative property, then we say that it is an abelian group. A special name we are giving, and that's called abelian group. So here Z comma plus is an abelian group because it is a group. We have proved that because it is a set with the binary operation as usual addition, and that all the elements or this binary operation satisfies the associative law, existence of identity and the existence of inverse. Apart from that, it satisfies the commutative property also. Therefore, this group is an abelian group, we say. Okay, so in similar way we can prove the second example also, that is set of real numbers is an abelian group with respect to addition. With respect to multiplication also, the r comma, so here the second example I am talking about, r comma plus is an abelian group. Similarly, r comma multiplication is also an abelian group. So this the students have to prove all these things. Okay, so coming to the next slide, I have to prove a very important theorem in the group, that identity element is unique. We have to prove this particular condition, that in a group identity element is unique. Identity element is unique. That's what we have to prove here. Okay, so before proving that, we must recall what is a group. A group is a set with a binary operation satisfying associative property, existence of inverse, and the existence of identity. Okay, and I already told you that there should exist only one identity, but each and every element should have the inverse. But identity is only one, not more than one in any group. So that's what we have to prove here. Okay, now let us prove by this diagrammatic way, and then afterwards we will prove by algebraic way. Okay, suppose G is a group here. Okay, G is a group, right? So in that particular group, suppose I am taking E and E dash are the two identity elements, I suppose. Okay, first of all, E I am taking an identity element, and E dash is not an identity element. So what I will have here, this is identity element, this is not an identity element. So E, suppose the binary operation I am operating on that, what I will get, E dash. Since E is an identity, I should have E dash. Okay, right. Now I suppose that E dash is another identity existing in this G. Then in that particular case, what I will have, E dash is an identity element and E is not an identity element. Okay, right. So in this case, what I will have E dash is identity element. Therefore, I will have E, because whenever the identity element is operated by the binary operation on some elements, we should have the same elements. Okay, but see the right hand side and left hand side. Suppose this is right hand side and this is right hand side and this is left hand side. Okay, left hand side. So what you said, right hand side and left hand side. Right hand side are equal, therefore left hand side must be equal. Right hand sides are equal, therefore left hand sides must be equal. That means what? E dash must be equal to E. So both elements are same. Both elements are same. That's what we have proved. Okay. So this is the way we have to prove that each and every group have identity and that is unique. That's what we have to understand. Okay. So how can we prove this here? Let G is a group. Let G be group. Okay, right, and E is a one identity element belongs to G, you suppose, and E dash is any other element, you suppose that also belongs to G. Okay, if E is identity element, if this is identity element, identity, which implies what we'll have is that E with some binary operation, let the binary operation be star defined on G. We cannot say that G is a group here. G comma star be a group. That only we have to say, but it is understood that some operation is there. Right. So E binary operation, the app operated on E dash, we should have the E dash. Why? Because E is an identity element. By the definition of the identity element, E dash is any element. Therefore, the reflection of E dash under this identity element by this binary operation equals E dash, the same element. So I am taking this equation number 1. Now, suppose that E dash belongs to G is identity element. Suppose, okay, is identity. Then what you will have? This implies now E is not identity as any element belongs to G. So what we have here is that E dash binary operation operated on E, you should have E, because E is any element, E dash is the identity element. The reflection of E under E dash operated by the binary operation, you should have the same element here. This is what equation number 2. Now look at that in the right hand side and left hand side. Okay, so equating the right hand side and left hand side, equality of 1 and 2, equation number 1 and 2, equation number 1 and 2, right hand sides are equal, therefore left hand side must be equal. Therefore implies LHS equal. LHS are equal. Therefore that must be equal to the RHS. Am I right? So O H Yes, RHS. Therefore, which implies left hand sides are equal, therefore right hand sides are equal. So E dash equals E, which implies identity is unique or same. Okay. Identity is unique. That is what we have to prove. Okay. That's what we have to prove. Right. So in the next class, I will take another theorem and we will prove that, how that works well. Okay. So thank you very much for your cooperation.